So we're going to do some just gravitation examples, some pretty straightforward ones, and then we're going to talk about the decaying orbit on question number 14 from the WebAssign. So the first one here, as you can see, you got an asteroid of radius 100 kilometers. The acceleration of gravity is 1 meters per second squared. That should really be a... Oof, that looks ugly. I'm going to fix it. Superscript. Okay. At the surface, what is the escape velocity you need to give a rock so it flies off? So it's kind of interesting here. Part of the reason I chose this problem is because, like, you think about a radius of 100 kilometers as being huge, right? This is a huge asteroid, all right? And it still has a fairly low acceleration of gravity, and we'll see what the escape velocity is for it. So acceleration of gravity being 1 meter per second squared, that gives us a hint. It means that, right, in the absence, in free fall, right, F net equals ma, which is equal to mg, right, is equal to g m over r squared, right? Both of these are downward, so I mean, I guess you could have the negative sign for both of them, but
battery low.
If I want to solve that, right, the mass of the object cancels out, and so I have 1 equals, right, 6.67 e negative 11 times mass of the asteroid over 100 kilometers, 5 zeros, squared. And this should give me a mass, and my mass is going to be, I might have already made a mistake. Quick, checking my math. I might not have put, I might have put 10,000, I might have put 10 kilometers instead of 100 kilometers. So this might be a very different value. Oh. Typed something in wrong too. Alright. Yeah, I did something slightly wrong, but that's okay. It's just going to alter things a little bit. This comes out to be 1.5 E20. Okay, so this is about 1/10,000th? No, less than that. 1/40,000th the mass of the Earth. Okay, so, I mean, it still seems big, but it's pretty small compared to the Earth. Alright, so we got escape velocity, right? And we know to find escape velocity, right, we're going to use the the energy equation, right? Kinetic initial plus potential initial equals kinetic final plus potential final, right? And the idea here is we want to get escape velocity, so potential final 0. We want it to barely reach that, so kinetic final 0. So I have 1/2 mv squared minus, and potential energy of gravity, right, is g m over r. 0. Again, my individual masses of my rock cancel out, which is good because I don't give you that information. So now I've got v squared equals 2 g m over r. And like I said, I'm going to have to do a quick little recalc here to get that value. So 67 e negative 11 times 2 times 1.5 e20 divided by is equal to 200. Okay. That's pretty big, but we're going to take the square root of that, obviously. And we get v equals 447 meters per second. So that's still pretty fast, but this is the kind of velocity, right, that you could maybe, like, if you could shoot a gun, which you can't actually shoot a gun because of combustion and on another planet or something like that, but this is a totally, like, you know, you shoot a bullet and it's never coming back down type of situation. Okay. Alright, so this one's a little bit quick here, right? We've got an orbital period of a new planet, half of Earth's orbital radius and twice the Earth's orbital mass. I guess I should say this is definitely in our solar system, so same sun. Now, we could do a lot of math here and do it, but I've got a better idea. I know period of the Earth equals 1 year. I also know that period squared is proportional to radius cubed. Okay? What that means is that the mass of this object is unrelated. Okay, it doesn't matter. All it matters is the fact that we've got this change in the radius. Okay, so basically what I'm saying is that if we have the radius of the Earth, so 1 year, right, squared is equal to, is proportional to, right, radius of the Earth cubed. What I'm going to do is I'm going to multiply this by 1/2, right? So I get the new period, T new, is proportional to, right, which means, sorry, I actually say that means 1 year is equal to, or is proportional to, raise the Earth to the 3/2, right? This T new is proportional to 1/2 raised the Earth, right, to the 3/2. This comes out to be 0.35 times radius of the Earth to the 3/2, right, which means that this is equal to 0.35 years. All right, and finally we have question number 14, which if you haven't looked at yet is a big question. It's got a bunch of information. It's about a satellite orbiting Earth. And just so you know, and we'll talk to it. I didn't want to write out the whole question. It's got a lot of parts to it. But for me, my mass of my satellite was 250 kilograms. And my altitude was, got it down here somewhere, 655 kilometers. Okay, so what that means first off is that I need to get my radius of orbit. Our orbit, right, is going to be 3 points, nope, not it. The radius of the Earth, right, which is 6.371 E6 plus that altitude, which is 0.655 E6, which is whatever that comes out to be. Did I write this down? I didn't write this down. 7.03. Yeah, 7.03 E6, basically. Okay, 7.03 E6. Okay, so to do that right, then I'm just going to go to, for A, it asks for my velocity, right? And for orbit, like this is a circular orbit, we can fairly assume. So it's just Fc equals Fg, right? Which is mv squared over r equals gm m over r squared. And that's going to mean that
powering off.
V is equal to the square root of g mass of the Earth over r, which is, turns out is 7540 meters per second. In other words, very fast, but that's okay. B, right, we know that period of orbit is just going to be 2 pi r. It's distance over velocity, right? We have the radius already. It's that big thing. We can plug in, and actually you should get something like 5,850, I got 5,860 seconds, which is 97.6 minutes. It wants it in minutes, so you got to divide by 60. All right, C is where it starts getting a little bit more. So I want you to think conceptually about what happens with this satellite. The satellite's getting slowed down. As it slows down, it's no longer got enough velocity to maintain that circular orbit, so it starts to fall. Now as it falls, right, and again, we're talking very fall, it's like spiraling just a little bit, but it is falling a little bit towards Earth. As it starts to fall, it gains velocity, right? Height change, gain in velocity. So as it's falling, it's also gaining velocity, which means which again puts it back sort of in its orbit again. All right, so we have this constant give and take, this change from kinetic, we're losing kinetic energy, but then potential energy is being transferred to kinetic energy. All right, and that transfer stuff is not very easy to do, which is why it's good that we can say that as long as it's staying in this general circular orbit, right, it's spiraling, but each loop of the spiral is still basically a circle, really close to it. We can model this with total energy. So we have total energy initial plus the non-conservative work equals total energy final. or mechanical energy, I guess I should say. Not total energy. Let's say mechanical energy. All right. And by mechanical energy, right, the mechanical energy of the orbit, we actually found. Right, we found the total energy of an orbit is negative g m over 2r. Right, because kinetic energy was positive and potential energy was negative, and so we add them together, we get that. So this is our initial. Plus, and the non-conservative work here is going to be, for me it was 1.6 E5. That was my per orbit. So I guess it should be negative that. Yeah, negative. That much work. And I had 1,300 orbits. Right? That's my negative. And this is just going to be equal to, right, negative g m over 2 r final. Okay? So I'm putting that together. I did the math out for this, right? So this term right here is negative 708.08 E9 minus 2.08 E8, and that's equal to, right, and I just put those together, it's negative 7.29 E9, and we're saying that's equal to negative G M over 2R final. And we can plug that in. And R final is actually, you just plug in and get R final. And my final R is 6.83 times 10 to the 6th meters. Okay? Now that's not my answer. This is like one of the ways people get this problem wrong all the time is they plug this answer in. This is radius. Altitude, right? So your answer, your altitude, is going to be that R final minus radius of the Earth, right? And that's going to come out to be 460 or so kilometers for me, depending on exactly how much you rounded. Okay. All right, so I need a little more room here. Delete all this, if I can. Apparently I can't delete it all. Come on. All right, there we go. All right, so part D, new velocity. Okay, this is the same thing as you did for part A. Okay, so it's just you're still doing FC equals FG, right? So I'm not going to plug all that in. You've got a new radius, right? We're using this radius now of the radius final, which was again 6.83 E6 meters, right? I'm just doing this over again. My velocity is 7640, which is a slight increase over what it was. It was 7540 or so, right? As it's falling, it is going to speed up. Even though we're losing a lot of potential energy, we are gaining some kinetic energy. Okay. Part E, again, finding the period. Period is still 2 pi r over velocity. And if you do that out, you got a new radius, but it's still pretty much the same. It's pretty similar, 93.5 minutes. Okay, similar value, but again, it's faster. It's moving faster and has a little bit shorter path. All right, F is where the part that has another bunch of problems that occur. Okay, it's difficult. So average force, right? Average force is going to be, if you have work, is going to be work over distance, right? So first of all, I've got the work, right? My work was 1.6 E5, negative 1.6 E5 over single orbit. So what's the average distance of an orbit? And that's where you got to be a little bit careful. So my radius initial was 7.03 E6, I think it was, right? And my radius final was 6.83 E6. Oops, that's not force final, it's radius final. Okay. Now the average between those, right, the average radius is going to conveniently be 6.93 E6, right? So that's my radius, which means my distance is, so this is 1.6 E6, I guess it's negative 1.6, but you're going to end up putting in a positive number in there, or E5. Okay, over the 2 pi r, and I got negative 0.00368, but I think it asks for magnitude, right? So, and you are going to put in a positive number. So my answer is 0.00368 newtons, as I should say. All right, hopefully those examples help. They're not an example of everything. This is pretty big. We'll have all the time in class on Monday to work on it, or Tuesday to work on it. All right.